This is an introduction and description of this interferometer, which is going down to the Antarctic. The trade name is EOCOM, EOCOM, manufactured by the NIWA Corporation now. This is actually quite an old instrument and was the property of the University of Denver. So they were using it about 15 years ago, I suppose. And we have refurbished it considerably and I think improved its performance, particularly by using it in conjunction with a modern PC computer. So we'll start off by briefly describing the instrument and then we'll progressively go into a little more detail. The instrument is a classical Michelson Fourier transform spectrometer. Energy comes in through the front of the system here, and we're particularly interested in making measurements in the infrared, and again in particular at about 12 microns, or around about 800 wave numbers. The light comes in the front of the instrument and moves and comes down on the optic axis and is reflected off a moving mirror which runs on these guides here, one guide on each side, which are on air bearings, so that there's very low friction in here. As well as the moving mirror, the second arm of the interferometer has a fixed mirror which is mounted over here. And between those two arms is a beam splitter, which in this particular case is made of potassium bromide, which is transparent to infrared radiation. So that the light that comes in here has several different parts. It comes through the beam splitter onto the moving mirror, back onto the beam splitter, and out here. Or alternatively, it comes here onto the beam splitter, onto the fixed mirror, and back out this exit port here. Now mounted out here is an off-axis parabolic mirror, and the energy is intercepted here by this off-axis paraboloid and focused onto a detector here. The detector is behind a window. In behind this ring is a very small 1 millimeter square surface area, approximately, mercury cadmium telluride detector, which is cooled by liquid nitrogen held in this dewar. And you just take this cap out of the top and pour liquid nitrogen into the dewar here. Okay, so that's the main interferometer. These two beams, the one coming off the moving mirror onto the beam splitter and out here, and the one coming this way onto the fixed mirror and back here, recombine in space out here to produce an interferogram. This interferogram is caused by the addition of all the wave fronts of light over a range of frequencies. And at one particular position of the moving mirror, which is down this end of the travel, energy of all wavelengths will be in phase. And this point is called zero path difference. We abbreviate this by calling it ZPD. And so as the moving mirror moves through that particular point, there is a maximum in the power of the interferogram. And I might be able to zoom in and show you that here, and how close we have to get Graham to be able to look at that.
Go back a bit, Gordon. Back a bit. Yes, yeah. Again, hold that steady there, Gordon.
So this is an interferogram which which shows what the signal coming out of the interferometer looks like as the moving mirror moves through zero path difference. And you can see that there's this oscillatory signal here, which suddenly goes up to a maximum and dies away again. Now the instrument is arranged so that we take samples at the start of a scan right out to the end of the scan, and in the present configuration we're taking something like 32,000 samples. The ZPD is occurring at about 1,050 of those elements out into the interferogram. So beyond this point there is a large amount of information of lower amplitude, and it is necessary to record all this information to maintain the resolution of the instrument. The shorter the scan, the lower the resolution. And this particular instrument, in the mode in which we're operating it, has a scan length of 8 centimetres, which gives us a resolution of 0.06 wave numbers. Okay. Returning now to the interferometer itself, the most important single component in the whole system is the beam splitter. And it has to be treated with great care because the potassium bromide material of which it is made is very hygroscopic. And so right at the outset we should say that the beam splitter has to be looked after very carefully. It has to be kept very dry. And so, for instance, a cold beam splitter should never be taken into a high humidity area because it will absorb the water and will become useless. Now, these are very expensive items. I mean, we're talking about many thousands of dollars and virtually irreplaceable. So we must emphasise great care with the beam splitter at all times. The beam splitter is kept in its own box down here, and it has a lid which seals reasonably well, and there are packets of silica gel which must be dried out from time to time in an oven and then put back in here. So we have spare bags of that silica gel. The beam splitter is removed carefully from its box. This is it here. This is the potassium bromide material, and you can see there is a window in the centre of that, and that window is to allow visible radiation to pass through. In fact, it is the radiation from a helium neon laser, which is used for controlling the data acquisition and the drive of the system. So when operations are started during the day, this beam splitter is taken out carefully out of its box. It has a little label on it to show you which is up, and around the beam splitter are several spring-loaded pins which spring-load it in position when it is put into the interferometer. So I'll do that now. The beam splitter is taken here and carefully slid into position like that and tightened up. Righto, now the beam splitter is in position and I'll describe the rest of the system. As well as the main interferometer, which you will recall uses the main moving mirror here and the fixed arm mirror over here, there are two other separate interferometers in the system. The first of these is the laser interferometer, which is used for generating the clock signals for the drive of the moving mirror, and also for generating the timing pulses which control the sampling to the computer. This is the laser here. It is a helium neon laser. Its output, the beam comes out this end of the laser onto a small 45-degree mirror which is on the optic axis, and it goes through the transparent region of the beam splitter and across onto the fixed mirror, the same mirror that is used for the main interferometer, and also onto the beam splitter and down onto the moving mirror. So it has a fixed arm and a moving arm, and is using the same mirrors as the main interferometer. The two laser beams recombine out at the front of the system and fall onto a small diode, and it is there that the laser interferogram is detected and generates a sine wave signal as the mirror moves, and the interferogram goes through maximum and minimum energy, with the sine wave period being equal to half the laser wavelength. As well as the laser interferometer, there is a so-called white light interferometer, and down here is a white light source which shines across here onto its own separate fixed mirror, passing on the way through its own little beam splitter, and then it goes down onto the moving carriage, onto its own moving mirror, so that on the moving carriage there is one 2-inch mirror for the main interferometer, and alongside it is a smaller mirror for the white light interferometer. And this white light interferometer, its detector is back around this side, and at one point on the scan the white light generates an interferogram, and this is used to control the start of the scan or the start of the sampling. It's a very difficult interferometer to adjust, and the way to adjust the white light interferometer and the main infrared interferometer is by adjusting screws at the back here with Allen keys. That's all right, isn't it? No, we're on ultimate. So we've described very quickly the main components of the interferometer itself. There are a large number of associated components which we will try and cover. One thing that I haven't touched on is that here is a filter wheel which is in the path between the off-axis paraboloid and the detector here. And mounted in that filter wheel at the moment is a bandpass infrared filter which allows radiation between 10.5 and 12.5 microns to reach the detector. If that filter weren't in position, the system would alias. In other words, energy from different regions outside that bandpass region would overlie the information that we're recording. The detector has been arranged so that it can be moved in the X, Y, and Z directions. Using these micrometer adjustments, so these can be turned backwards and forwards to give very small adjustments of the position of the detector. And when the system is being aligned, the interferogram, by adjusting the fixed mirror over here, will be moved slightly in space. And so alignment is an iterative process. First of all, we align the interferogram in space, and then we make small adjustments to the position of the detector by adjusting X and Y. Then we realign the interferometer slightly, then readjust the position of the detector, and finally adjust the focus, which is movement of the detector this way. The signal comes out of the detector via this BNC and cable down here and into the preamplifier. The preamplifier has two helipod controls on it. This one here is for detector bias. This changes the bias current through the Mercad-Tel detector to optimize its performance, and we are currently running that with a dial setting of 950, which is equivalent to roughly 40 milliamps of current through the detector. This helipod here controls the preamplifier gain, and we try and run that as near to maximum as possible, but we use that to fine-tune the gain of the system to try and maintain the output overall voltage of the system at something like 20 volts peak to peak, and I'll get onto that a little bit later on. So there we have described most of the workings of the main interferometer. The only other feature, I think, is this switch here. This is the on-off switch, which controls the interferometer drive to start the system scanning. It must never be turned on unless there is air of sufficient pressure running onto the air bearings. Now that air is generated by a compressor, or alternatively it can be provided by cylinders of compressed nitrogen, which is the way we're operating it at the moment. But in the Antarctic, it would normally be provided by a compressor. There is a cutout in the EOCOM electronics, which also operates a pilot light on the front of the electronics bin to show when the air pressure has reached the required level, which is about something under 100 kilopascals. So we always try and provide air at 100 kilopascals to the air bearings, and again we'll come on to that later. Now moving on to the rest of the system, the light comes into the front of the instrument down this tower. On the roof we have a computer-driven sun tracker, and you'll see that in operation shortly. Light from the sun tracker is made to come vertically down onto this 6-inch spherical mirror. The beam from the spherical mirror comes up here and through a small aperture stop here. This aperture stop is at the focus of this mirror, and so the image of the sun, which is our light source, appears on this aperture stop. The beam continues through the aperture stop and onto this top spherical mirror, which has half the focal length of this one, and then comes down as a more or less parallel beam onto the 45-degree mirror, and then out horizontally and into the instrument. Now these mirrors all have to be adjusted so that the input beam is vertical onto this mirror and horizontal out from this mirror, and also on the optic axis. So the beam has to come into the interferometer, through and onto the moving mirror, and fall back on itself on that same path. The adjustments are not difficult, but a bit time consuming. We also have a gizmo here, which is a lash up to enable us to see the image falling on this aperture stop from some distance away, so that we can control the tracker from the computer and see an image of the sun and the aperture stop on the screen here. Righto, we'll move on to other components of the system now, I think.
Yep.
Okay. You filming?
Yes.
Moving now on to the other components of the system. This is the main electronics rack, which has a large number of cards in here, which process the signal from the main interferometer. The signal comes over via a large multi-core harness and goes through filter amplifier stages and finally into a high-speed analog to digital converter, and from the ADC it goes out to a PDMA board on the compact computer, via that board the interferogram signal is stored in the computer memory. Now, just looking at the front panel here, on the left, this BNC is called the infrared signal, and we normally have that connected to a storage oscilloscope, a digital scope, which is on the bench over here, storage scope, and also we have it connected to an audio amplifier so that you can actually hear the interferogram, and this is useful for alignment purposes. The next BNC along is labelled laser analog signal, and we normally have that connected to a second small scope so that the amplitude of that laser signal can be maintained. The fourth BNC along is labelled started scan analog, and that is the point at which you can monitor the white light detector operation. So we normally either connect the storage scope to the infrared analog signal or the white light analog signal to adjust those two interferograms. Now, along here are a number of thumb wheels. The first of these thumb wheels is this pair here, labelled velocity. The normal setting for those is 36, and this velocity controls the velocity of the scan so that one scan occupies approximately 10 seconds. The next thumb wheel along is labelled sampling space, and it is normally set at 5. This controls the sampling by determining how many zero crossings of the laser there are between samples. And we arrange that sampling so that during the 10-second scan we're taking 32,000 samples. The next thumb wheel along is labelled length, and the normal setting for that is 8 during operation. This is a full length scan of 8 centimetres, which gives us the maximum interferometer resolution of 0.06 wave numbers. Now, reducing that by 1 to 7 halves the scan length from 8 centimetres to 4 centimetres, and reducing it again to 6 halves that again from 4 centimetres to 2 centimetres, and so on. Now, when we are doing preliminary adjustments of the white light detector or the main interferogram, we usually set the thumb wheel switch to 4, which gives us a very short repetitive scan, and that is helpful in alignment, as I'll show you later on. To the right of that are 2 thumb wheels labelled high and low pass. Now, these are the filter settings for the analog signal, and the settings of 2 and 3 filter the give you a pass band between 500 and 2500 Hertz for the analog signal. The next thumb wheel to the right is labelled GCP, and it is set at 3. In conjunction with some thumb wheel switches on one of the boards inside, this controls the position at which the gain is switched during a scan. The interferometer gain is increased by a factor of 8 at a point just beyond the main interferogram to maintain the amplitude of the signal right out into the wings of the interferogram. And so in our particular case, the main interferogram occurs at something like 1050 sample points out from the start of the scan, and the gain is switched by a factor of 8 at sample position about 1150. And the last thumb wheel here is the gain switch, which is currently set at 4, which controls the output voltage to the computer. And changing this by 1 doubles or halves the gain. So if we take that from 4 to 5, the voltage, peak-to-peak voltage of the output signal is doubled. Taking it from 4 to 3 will halve that signal. Introduction is this here, which is the unit that controls the sun tracker. The electronics provide stepping pulses which control the azimuth and elevation stepping motors on the sun tracker mounted on the roof. And there are 3 parts really. This unit here takes pulses from the computer and converts them into a suitable form to drive the stepping motors. This unit here contains resistors which are in series with the drive motors, and this is the computer interface unit. And the remaining component part of the equipment is the actual computer, which is here. This is a compact 386N, and we'll describe that in more detail later. But before we do that, we'll now move on to the roof and look at the sun tracker and describe the optical alignment process. This unit is the sun tracker, which operates under control of the computer, and drive pulses are sent to the elevation motor here, which drives the elevation mirror here through this gearbox, and also to the azimuth drive motor, which is underneath the turntable and drives onto a gear underneath this top surface. Light from the sun comes in onto the elevation mirror, is reflected onto this mirror, and then goes down the optic axis of the system. To ensure good tracking, the sun tracker must be level. And to do that, you turn the switch off below the tracker here, which disengages the clutch and enables this to be turned. And using this special level, you level the turntable on orthogonal axes here and here by using the adjustment screws that are on the triangular mount which supports the tracker. Assuming that the turntable is now level, we are ready to align the whole system. To do this, we use this laser for alignment. First of all, grab hold of the coupling between the gearbox and drive motor and turn it around so that the elevation mirror is vertical. You can do this by lining it up against the vertical support for the second mirror on the tracker, and turn it round in such a position that by adjusting the height of the laser here, we can shine the beam onto the elevation mirror and off at right angles onto the second mirror and down the hole. At that point, we can put in this alignment device, which has 3 pins on it to center it into the hole here. That's pushed flush down onto the table. It has a small hole in the center. And then we adjust the azimuth, the elevation and the height of this laser so that the beam is going into the system and straight down the small hole in the center of that alignment plate. Now, under normal circumstances, to get the sun coming down on the optic axis, having leveled the turntable, with the clutch disengaged, you just turn the whole turntable around and then adjust the azimuth and elevation mirrors manually like this. Until you can see the solar beam symmetrically on the entrance aperture of the tracker, like that. And having done that, re-engage the clutch by turning on the switch. That's it. We'll now run through the general setup and operating procedure, including the optical alignment. The first thing to do before you start a run is to fill the detector with liquid nitrogen and let this settle down for a few minutes before you start. And so I will begin by just topping up this detector. Now, for the first run of the day, you might need something like a half or 3/4 of this thermos full of liquid nitrogen. But after you've been operating, you will just want to top it up with a small amount every hour or two. And so I'll nitrogen into this thermos. Make sure that the off-axis parabolic mirror here is covered, and that you have a sheet of cardboard covering all this general area to stop liquid nitrogen running down over the optical components. You then take this little filter, this little funnel, and pour the liquid nitrogen into the detector like this. You will hear it boiling when the viewer is nearly full. Don't handle the funnel. We're now ready to install the beam splitter. So carefully remove it from its box, and having done so, put the silica gel back in the box and shut the lid. Now insert the beam splitter very carefully. Push it right home and do up the locking screw. You must make sure that there is liquid nitrogen in the detector before you ever turn on the preamplifier, because when the switch goes on and the power is on the EOCOM electronics, the bias current flows through the detector. So we now have the coolant in, we have the beam splitter in, we turn on the main electronics, which is the red switch on the electronics panel, and you'll notice that the laser comes on. At this point you can remove the cover off the off-axis paraboloid, and now make sure that compressed air is flowing through the system. So this is the compressor is on, or else you have gas coming from the nitrogen bottles. So I've turned the gas on, and we are now ready to start a scan. So we can turn the switch on, and the scan starts. And to do the first alignment, we will shorten the scan by changing the length switch to 4. We can now adjust the switches on the tracker to get the sun coming through the system. Coarse adjustments can be done by using the electronics here. Fine adjustments can be done by using the keyboard, and we'll get onto that in a moment. So I'm now moving the solar beam into the center of this mirror. By adjusting these switches on the tracker electronics. And you can see from the image on the screen that we are quite close to tracking. At this point, all the switches on the tracker electronics should be in the up position. And we now have the computer program running so that we are tracking in elevation and azimuth. And fine adjustment of the sun position can be done by using the function switches F6 to F9. These control the elevation, F6 and 7, and F8 and 9 control the azimuth. So now, with the computer program running, we're ready to align the system and then acquire data. So we have the interferometer running on a short scan. If you look at the white light source in here, you'll notice that as the instrument is scanning, the white light is going on and off. And this is the correct mode of operation. If, for some reason, a maladjustment of the controlling laser or the white light detector itself, the white light will not flash on and off, and the scan won't function properly. But at the moment, the white light is going on and off, and we can look at that on the oscilloscope here. You'll be able to get that, do you think, Graham? To monitor that signal, the oscilloscope should be plugged into the analog start of scan B and C. And you can see on the storage scope that we're getting something like something over 4 volts peak to peak. Now this is the white light interferogram, which starts about 1,000 samples before the main interferogram. And so this has to be maximized using the Allen key adjustments on the white light detector mirror. Looking in from the back, it is the right-hand set of Allen keys and the two closest to the center. And so very, very carefully, these two are adjusted here to maximize the signal on that scope. Now this just requires considerable practice. The adjustments are very, very small indeed. I'm not actually going to make the adjustment at this point. But if the scan is not running properly, the first thing to look at is the operation of the white light detector. Okay. While we're on this short scan, we also want to monitor the laser analog signal. So a B and C should be connected to the second point on the control panel. Analog laser onto this scope, and here we can see the laser signal as the instrument scans. We should be getting something like 1 or 2 volts peak to peak on this signal. Righto, we will now look at the alignment of the main interferometer. We are now around behind the casing which holds the fixed mirrors. Of particular importance here are the main mirror, which is directly behind here, and the white light detector mirror, which is behind here. Now the two adjustment screws for the white light detector are these two right in the center, and very small adjustments of those will change the white light interferogram. We are now going to try and make the alignment of the main interferogram, and to do that, Allen keys are inserted into these two here. We'll now do the main interferogram alignment, we have the analog B and C connected to the storage scope and the interferometer running on this fast scan, and here we have the interferogram that we're looking at. Zero path difference is where this signal is at a maximum, and what we want to do now is to align the interferogram and also align the detector. So to start with, by adjusting the function keys on the computer keyboard, we center the solar image on the aperture stop, which is up on the tower, and observe the interferogram here on the storage scope. What we want to do now is to peak this signal. So this involves aligning the interferogram using the adjustment screws on the main mirror and also adjusting the position of the detector. So I will move the detector on its various axes and you'll see how the signal goes down. You have to watch the scope triggering and make sure that this light here continues to blink, which tells you, of course, that the interferogram is being upgraded. I'll now try and peak this. It's about there. Now on the other axis. That's a maximum. I'll now adjust the interferogram by holding one of these Allen keys and moving the other. And now it seems that the interferogram is reasonably aligned. When it is, the pattern on the scope is symmetrical. Although I see in this particular case, if you look at it here, you'll notice that the amplitude is higher in the wings here than it is at this point here. So I'll try a further slight alignment here. And in fact it was misaligned. You can see that we now have a much more symmetrical interferogram. I'm just adjusting the triggering here. Another tweak on the alignment here. You'll notice bad distortion there. It shows that we're overloading the system. So we decrease the gain from 6 to 5 and carry on with the alignment. And repeat this process iteratively, adjusting the interferogram here and the detector with these controls here until we maximize the signal. have now aligned the interferogram. You can see that the whole interferogram here is quite symmetrical. These little side lobes, either side of zero path difference, are quite symmetrical, and you have this classically shaped envelope which you will come to recognise. We are running here at 1:30 New Zealand Standard Time, so the sun is quite high, and with a high sun and everything aligned, we get around about 20 volts for a gain setting of 4, and with the preamplifier and the bias wound almost right up. I'll just check here, the bias is set on 950, and the gain, the preamplifier gain, is on 4. And I see on the scope here that we have about 18 volts peak to peak of signal. And so that is very adequate for acquiring data. Okay. We're now in a position to be able to acquire data, and the program here, the software was written by Paul Johnson, is menu driven. Key F2 when ready to enter data acquisition file details. So before we do that, we will now adjust the scan to its full length. So we change the length switch to 8, so that the switches, once more reading across from the left, should read 36, 5, 8, 2, 3, 3, 4. We're now ready to acquire data, so we press F2 and get the prompt EOCOM binary data file name. Now this will be a sequential 2-letter file name. I'll call this one XX, and we will acquire 5 scans, 1 to 5. The computer software will now acquire these scans, and it will inhibit the tracking while the scan is in progress. So the scan will start, it will take a file, update the tracking, take a second file, and so on. And what we want to do ultimately is to co-add all these scans to improve the signal to noise, and then Fourier transform the co-added file to produce the spectrum. What you have to do now to start acquisition is to press F2 again on the flyback of the scan. So we let the mirror come right out on the scan, and on the flyback hit F2 now, and you can see the numbers which are going into computer memory. Second scan starting. And you'll hear the bump as the tracker updates. Now, while data is being acquired, you just want to keep an eye on the scope, make sure that it's triggering. You can see the light flashing when it's triggering, and we want to log the peak-to-peak volts, the gain switch setting, and the preamp gain and bias settings. We have now acquired 5 scans there, and for demonstration purposes, I'll now process one of those. If I hit escape, we will shell out of the DOS program, and we can then run a program called FTIR, which will enable us to co-add those various spectra. It will then produce one binary file. In this case it will be called xx.bin, which we can then process with a program called FT. XX cut. We got a bummer because it wasn't the right file name.